Hello, everyone, and welcome to this Micromaterials mini symposium. I am Dr. Sam McMaster. I'm from Surface Ventures, and I'm here to help run the event today. So you will be seeing me occasionally, but won't be hosting. I'll be bringing our host, Dr. Krishna Rain, on stage in a moment. I'm just here to deliver a little bit of technical info about how the event is going to run. We'll be aiming for approximately 2 hours for this event. We'll be taking questions for each speaker specifically. So during the talk, please type those questions into the chat. I'll be marking them for the Q&A, which we'll do directly after each speaker. Throughout the event, I'm going to be releasing poll questions and handouts from Micromaterials, so you'll be able to answer that. We'd love to find out some more about you and also to give you some informational brochures. We'll be releasing some attendance certificates later in the event, and for everyone that's registered, you will be receiving, an email containing a link to watch this event back as a replay. Okay, so for now, let me go ahead and bring Krish on stage. It'd be great for everyone to say hi and tell us where you're joining from in the chat whilst we're loading.
Good morning, good afternoon, or good evening, depending on whereabouts in the world you're joining us from. My name is Krishna Rain. I'm director at Micromaterials. Thank you for joining today. We do appreciate that it takes time. I hope you will find this seminar to be useful, interesting, and informative. I would just like to start by just giving a couple of thank yous out, particularly to Sam for his organisation, and to the Micromaterials team, Alison especially, for the work they've done on this seminar, and to our speakers, of course, for the talks they're about to give. I would also emphasise that if you have questions, please do put them in the chat box, as Sam was indicating. It's very useful to have those questions. We will answer as many of them as we can, and the ones we can't, we will put out by email to the speakers, so they have the option to answer you in due course. If you like this seminar, please do go to our LinkedIn page and follow us at LinkedIn. It's the best way to find out about future seminars of this nature, as well as new publications, new literature reviews, and things like that, which are always on our LinkedIn page. So I would like to start off by talking about the Micromaterials, basically. Who are we? I've got a very short introduction to us before we get to the talks. For those of you that do not know us, we are based in Wales, which is tacked onto the side of England, and so we're somewhere between Manchester and Liverpool, if you do know the UK geography. We were established in 1988 by John Smith, and we've been in the nano-indentation, nanomechanical business ever since. We have a very stable, very long.
Excuse me for the slight technical issue there. Let me just try to get Krish back on stage. Everyone. It's a good point, Ben. Perhaps England is tagged onto the side of Wales. Krish, are you able to come back on stage?
I don't know how much you missed. Did you miss much?
I think you just said about England and Wales being tagged onto each other.
Oh, okay. So we did that slide. So we did the next slide. So I was basically just bringing up Ben's picture here as the leader of the applications team. Huge experience in our team. So good place to come and ask questions and find out about nanomechanical measurements, basically. Our product range, our ambient standard system research tool workhorse is the Vantage. It's a multifunctional, multi-scale, highly configurable, multi-environment instrument. It complies with the ISO standards that I'm sure you'll hear about later, and it has yeah, everything is over 30 years has been developed into a truly multifunctional instrument. We are known particularly for environmental control, whether that's, as you see here, putting things into a plastic glove box and controlling the environment, or putting the whole instrument into a vacuum chamber. This allows us to get up to 1,000 degrees centigrade ultimately. We're pushing that envelope all the time, of course, but it allows us to do very unique things. Hopefully you hear some of that from our users. We also are fairly unique in as well as indentation and scratch. We also specialize in impacting. So taking the probe off the surface and repeatedly hitting the surface. Again, if you're interested in that, there won't be so much of that in the talks today, but you're always welcome to come and ask about that. That's a rather better picture of our system in the vacuum. Some of the work that you'll see today has been done in that. Some of that's been done on the Vantage system, with the often with the purge chamber option. But what I want to emphasize here is that's a full indentation system inside the vacuum, working up to 1,000 degrees centigrade. Indentation, scratch, wear, impact. It's a full system in there. It's not a modified SEM type of indenter, and we can put the nano positioner, we can scan and everything inside there. Yeah, we're used around the world. That's my standard marketing slide. But yeah, and yeah, thank you for attending this. I thank you from the whole team at Micromaterials. I trust you will find it useful. I trust that the talk will be we were expecting. We have 4 speakers today. The first speaker is Nigel Jennett, followed at 2 o'clock UK time by Vinay from the Canadian Nuclear Labs. Then following that, we have Lucas speaking from NCBJ in Warsaw. And finally, James representing the UK Atomic Energy Authority for the Culham Labs in the UK. So without further ado, I will hand over to Nigel. Nigel is the director of the Strategic Measurement Consultants. He was previously professor at Coventry, but probably best known in this business for his work at NPL for over, I think, 20 years plus. I forget, Nigel, you can put the detail on that. I lost track certainly, and the work he did particularly well known for his standardization work he did there on the ISO standards, but many other things besides. So I wouldn't like to pigeonhole you. Nigel, without further ado, I'd like to hand the stage over to you.
Thank you very much. Just excuse us a little moment while we make the necessary adjustments. I will have to share a screen, which is very exciting.
Make sure that everything goes smoothly.
Magic button.
Okay. To the members of the MML team that are watching, lovely, I can see that. There is a question from Samir in the chat about the maximum velocity of the impact with a nano impact tester. Perhaps you would be best placed to answer that. Okay, Nigel, I can see your slides. Please take it away.
Thank you very much. So today's talk's about the challenges in high temperature instrumented indentation testing. And I'm coming to you basically as the chair of the ISO committee that maintains the ISO 14577 series of instrumented indentation standards. And also, as Krish kindly pointed out, my 23 years at NPL, about 7 years as leading a group in Coventry University, all of which has been developing measurement methods for materials testing. So let's look at high temperature testing, if I can make that work. So today I'm going to be focused on the nano instrument style instrument. This is based upon work that was done in the last decade at the National Physical Laboratory, where it's a nano test that was principally used for the early work. And some of the slides I'm presenting here are slides that have been presented before by myself when I was at NPL, but giving some detail. And some of them are results from a European Metrology Research Programme called T3D, which specifically looked at what we needed to do in order to put in place a new draft standard or a new standard for elevated temperature instrumented indentation testing. So there is a draft. It's called committee draft, that's the CD. So ISO CD 14577 part 6. The scope is that it's for elevated temperature, instrumented indentation test at elevated temperature. And that is defined as a machine where the test piece and the indenter is heated above ambient conditions to a controlled and measured temperature. And insulating shielding is used to enclose the hot zone so that the instrument and sensors are at ambient temperature. So that's distinct from operating the entire device in a furnace, which it does not cover by the standard. So I always have to say this because you know, ISO 14577 is the instrumented indentation standard. It allows you to measure a whole range of things, but in order to do that with reproducibility and with accuracy, and you need to be able to do the correct SI traceable calibrations. So you need to calibrate force, you need to calibrate displacement. Increasingly, as we start looking at dynamic indentation and creep rate measurements, we are starting to have to measure and calibrate time in an absolute way. But of course, we need to do indenter area function. That's the whole principle of instrumented indentation, is using area function, and instrument frame compliance. And then when you make a measurement, with all of those things set up, they are fixed. But for each indentation you do, you've got your environment at your sample, and you then have an individual indentation thermal drift rate. And depending upon what you're measuring, you could very well have some indentation creep. And as you go to higher temperatures, that's more and more likely to happen, because creep is a thermally activated diffusion process which allows continuous displacement at a constant stress. And you have to look at each indentation to be able to decide where the indentation started. So there's a 0 point you have to define. For standardization to be reproducible between instruments and between users, you have to have traceable calibration. So traceability of your calibrations to the SI is fundamental. And to inform yourself of the repeatability of your machine, to be able to do some of the calibrations of frame compliance, etc., you need to use certified reference materials. And for the full validation of the instrument, you need to have 2 of those with sufficiently separate properties so that you can obtain a low uncertainty frame compliance and a low uncertainty area function without having a sort of circular argument, because you need both to do both. Moving on to high temperature though, what's the challenge? Well, there's some new requirements. Pretty much you have to do everything that you used to know you have to do, but now you have to do it as a function of temperature. So the challenge is instrumented indentation testing, traceable calibration as a function of temperature. Now, before you start, you've got issues about, well, okay, you've got high temperature, so there's a whole bunch of new considerations you've got to look at, and we'll talk about those. Then you've got the issue of, well, you've got a really hot zone now. How do you get a calibrator inside a hot zone to be able to measure force and displacement? Well, you can't, and that's the point. You have to be able to measure outside. And then, well, now you've got a lot of very different conditions. You've got oxidation, you've got very high temperatures that will change the properties of materials. You now have to have your certified reference materials able to be certified as a function of temperature. Those are pretty much the 3 key challenges, of which we will talk about each of those in turn today. Well, let's start with the valid method. Well, okay, so you've got a high temperature hot stage. It's got to be isolated, so insulation is essential. Okay, this is the Mark 1 style hot stage that we had many years ago, and it's quite simply a wire wound furnace with some insulation around the outside of it that you stick a sample onto, and that's the representation of there. The iterations of this stage got to the point where we had a sliding heat shield in order to stop the heat getting out, because if you don't have a heat shield, you've got something that goes up to several hundred degrees centigrade inside the environmental enclosure that you carefully bought to keep the lab temperature out at 23 degrees centigrade. So you've now got something that's pumping heat out into your very carefully controlled environment and will therefore cause potentially a lot of problems. So you want to stop heat getting into your system. So wherever there is a path out of the hot zone into the instrument, you need to stick an insulator. So thermal breaks in the indenter shaft are a good idea, and sticking a shield on the outside of the hot zone reduces the temperature of what the inside of the machine sees. So you probably can't quite see the temperature here, but this bit here is around about 40 something. If out here, and this bit here was about 75 degrees, you cover it with an insulator and you can see the mid-range of that is around about 30 degrees C. It's not the same temperature as the instrument itself, and there are some issues, particularly in vacuum, where you might need to take the heat out actively, because what you really want to have is no heat input into your carefully maintained instrumental environment. Take-home messages: thermal drift, calibration of your indentation system are all driven by the same things that there were at room temperature. In other words, a change of temperature of the environment will cause changes to those things. So you still have to control that. And you should not, in your mind, link necessarily what's happening inside the hot zone to the creation of thermal drift, even though that is a hot thing. It's the leak of heat from the hot zone, generally speaking, which causes you the problems. So standard nano indentation, you apply a force, you measure the displacement, and you get a force displacement curve. And we know that there's a compliance of the machine, which is a displacement that's a function of the force that you apply to the frame of the machine. And you calibrate that so that when you do the force displacement curve and get the green upward and the blue downward curve, you can then correct it back to what it would be without the compliance. But you can see that the actual displacements at zero force are the same with or without correction, because that's the nature of frame compliance as a function of force. The killers are thermal drift and indentation creep, or viscosity. And we'll talk about it in terms of drift and creep today. So what does that do? Well, at a constant force, it increases the measured displacement, which suggests that you have a bigger hole, which suggests that the elastic modulus is changing and the hardness is changing, even though you haven't done anything. Well, that's not right. If you take the force away, you still retain that drifted displacement value, so there has to be a correction. And typically you measure the drift rate and you correct it at room temperature by using various hold mechanisms. In the worst case scenario, you have a creep rate as you unload, which is so high that you're creeping faster than you're unloading. And in those circumstances, you end up with a stiffness error. And that can actually give you a negative stiffness and therefore an apparently negative elastic modulus. But unfortunately, you won't get a Nobel Prize. It is just an error. So the question is, what do you do about that? Well, the standard says quite simply that you wait until the drift rate is low enough or the creep rate is low enough, and then you can unload. And low enough means that you have the option of increasing the force removal rate so that you beat the creep rate and then get a valid stiffness measurement. However, increasingly, we're looking in the standards committee at using elastic modulus as an internal reference in each of the standards, and use that in a way so that we can actually determine what's happening. And this is not a new idea per se. It's been knocking around since Jocelyn and Oliver tried the P/S squared methodology to try and get rid of the area function. But the point is this: if you want to wait until a huge instrument gets to absolute thermal equilibrium and has zero drift, you'll be waiting a long time. You can do it. We did it at NPL. It's over the first day or two, we got down, and over the last day or two of the 5 days we ran, we got down to femtometers per second. It can be done in a temperature controlled laboratory, but nobody has that time to do a single indentation sensibly. So what do? The best use of time is to stop thermal drift happening in the first place. And that is a question for manufacturing, but it's also a question for your design of the experiment and how you set up the experiment so that you have the best thermal insulation and you don't cause drift in your own instrument. Then after that, it's using a high force removal rate, which is the obvious thing to do, because the faster you unload, the less error in absolute drift you get, whether it's drift or creep. Then you've got elastic modulus correction, which says, well, if I know the elastic modulus, and we know that it doesn't really change that much with creep or thermal drift. So if I look at the elastic modulus, I can say whether I can reverse the equation, in fact, and get out the size of the indentation that must be there for the stiffness as I measure to give me the correct elastic modulus. And therefore, I can use elastic modulus correction as a way of tracking the actual increase in the contact size, and I can compare that with the actual change in the displacement rate and start to separate the drift from the creep in my indentation experiment. However, word of warning, and the reason the Jocelyn and Oliver P over S squared method is not a preferred and widely used method is that, particularly for metals which are very stiff and have a very steep unloading curve, S is very variable, and so there's a very high uncertainty in this, but it is a way forward if it's the only thing that you can do. So we've got a method. The question is this: we're going to high temperature, so should we still be using the same indenter? And there's a lot of positive things you can say about diamonds, and there's a lot of things that we just take for granted in instrumented indentation because of that. And that is what we see here. It's got potentially a high melting point. It's got very good thermal conductivity, very low thermal expansion. Seems like a good idea. But unfortunately, diamond is a metastable material, and it starts turning to graphite, and that gets faster and faster with higher temperatures. And by the time you get to 300 or 400 degrees Celsius, it's a big problem. Now, it also forms carbides, and so you can cold weld to your sample, or you can wear away your tip, or you can damage your sample. And of course, it oxidizes, and you have the potential of making an extremely expensive contribution to global warming by creating carbon dioxide by burning your tip. Now, it doesn't take an awful lot of material removal at the very tip of an indenter to radically change the area function. So whilst this might seem to be a small problem, it is actually a small problem with quite large consequences, and therefore you have to think what to do. So in ISO 14577 part 6, there's a list of very hard things which you might try to use as an indenter instead of diamond. Sadly, nearly all of them oxidize at some point or other. However, you do have some temperature limits that are a bit higher than the 300 or 400 degrees Celsius of diamond, and so you have an opportunity to do higher temperature indentations. Of course, sapphire is already an oxide, and so it doesn't oxidize, and therefore it's a strong contender, if you like, to start as you mean to go on, if you like. The difficulty is this, though, that all of those materials are lower modulus and lower hardness, and therefore they place limits on what you can actually test. And the equation that you use to calculate modulus uses the correction for the indenter response, and that's very small for diamond because it's got a high elastic modulus and a low Poisson's ratio, but it's not if you have a normal a material like sapphire. And so then you need to know the values for those elastic modulus and Poisson's ratio very accurately, because the uncertainty goes up if you don't. And it's got a lower thermal conductivity, and we'll see that there are some consequences for that. And of course, there may be different production challenges. And one of those is that, can you stick it into an indenter body with a low compliance and a reproducibly low compliance? If not, then you're going to have a rickety indenter, which is going to give you variable results. So moving on, we've got part of the way, and I'm still looking now at how do we just look at the calibration. Well, that's quite straightforward. We do exactly the same as we did before. In our case, we used an interferometer. We monitored the movement of the stage, which pushed the indenter, which changed the capacitor spacing, which measured the displacement. Great. So you think, well, it's all at room temperature, so why is there a problem? Of course, it's always best to try. And what we found was that as you change the temperature of the hot zone, we got around about a 5% change in the displacement calibration. This is not thermal drift, this is an actual calibration change. So a nanometer is no longer a nanometer at 500 degrees Celsius. And that's a problem, because the limits on displacement and force calibrations in the standard are about 1%, that sort of order typically. So now we're talking about having to calibrate your system as a function of temperature. And Now you say, well, okay, so that requires access to an SI traceable calibration device. Do I have one of those? And you might say, well, actually, what I have got is a stage encoder, and I'll use my stage encoder values and calibrate against that. And unfortunately, to do that, you have to calibrate your stage encoder. And I strongly advise you SI traceably calibrate those, because they're not intended to be absolutely correct measurements until they have a calibration. And in our case, there was a 5% error, which we would have had to correct it if we were using the stage encoder results directly. So word of warning on that one. Moving on now to the thing that's new. This is completely new: temperature. Instrumented indentation didn't bother about temperature as long as you were in lab temperature and it was constant. Now you've got a temperature. You now got to measure the temperature. You now got to be able to assign a temperature to the mechanical response that you're measuring at the contact point. Because let's face it, the strong contribution of instrumented indentation is the ability to map things. So you want to be able to look at the temperature exactly where you indent, not at some distance away and hope for the best. So let's have a little think about thermodynamics. It's a new thing, temperature. We're mechanical people. We're not really thought about temperature, and we have to think, well, what is temperature? Temperature is in fact the measurement of the energy level in a material. In terms of vibrations, and the thermal conductivity of a material is the ability to conduct that energy through the material. If you have a thermal conductivity of K, you measure it by measuring the heat flow for a particular temperature distance across a particular distance in the material. That's how you do it. And now, if you rearrange that equation, what you see is that the temperature difference that you see, which could be from a heater to a surface, a heater to a tip, the inside to the outside of an insulator on your hot zone, now depends upon the thickness or the distance L and the thermal conductivity, and then you get the power that is taken out. So if you put insulators in the way, you can reduce the power for the same temperature difference. And that's, or the temperature difference that happens for a particular power that's taken out, you've got the fixed power that you're taking out, is dependent upon the thermal conductivity. So thermal equilibrium is the state of constant heat flow. So the diagram above is in thermal equilibrium, but at no point in that article there is the temperature the same as at any other point. So it is not, thermal equilibrium is often loosely used as a term, and it's not. So the difference T1 to T2 is only 0 when the heat flow is 0. And at that point, you can say you've got thermal equilibrium. So how do you measure it? Well, stick a thermocouple on it, obvious, right? So if you put a thermocouple in the middle of a sample and a thermocouple at the edge of the sample, would you get the same reading? The answer to that is no. And that's because you get radiative losses. So heat radiates away from a hot thing called black body radiation, and the edges lose heat and get supplied from the center. So the center tends to be hotter than the edges. And you can see this quite clearly if you put two thermocouples on a piece of steel, which is a pretty good thermal conductor. You can see that at around 100 degrees, you get a fraction of a degree, and it goes up to 5 degrees at 400 degrees Celsius. And that's just over a centimeter or so of, or half, possibly, yeah, a centimeter or so of steel on a hot thing. And people sort of think, oh, okay, 5 degrees, maybe that's not so bad. But this is the issue is, how do you actually attach the thermocouple? So if you've got a piece of steel, then the temptation is, well, just spot weld it. That's what we would do. And then you get a very intimate thermal contact, and that's quite a good idea. So if you have a heater, a couple of thermocouples, you've got this radiative loss at the edge, which means the edge thermocouple is cooler than the center thermocouple. You've got your indenter, it's also emitting. And when you move one into the orbit of the other, then the input energy from the other heater, it increases the energy level that you have on the surface above what it was when it was far away. And so the temperature of the surface for the same powers in both of those heaters goes up, because the energy balance, which gives you the energy level, which gives you the temperature, has changed. If you put those thermocouples on using a glue, like a so-called high thermal conductivity cement, which is not really that high thermal conductivity compared to steel, for example, you can see that you're likely to get a thermal break here, which causes a temperature difference, and you do. So you do the same thing again, move it into the case. In this case, now the thermal energy that you're receiving here heats up this very small thermal mass, and it's got to conduct that heat away into the body, and it can't very well, and so it heats up. Okay, so I'm running out of time, but what I'm going to show you here is that if you have the stage far away, you think you've got 400 because you dialed it up on your heater. You in fact have 350. If you put cement in the case, you might have 340, but you'll be indenting into the steel. So you've got a 10-degree error there already. And if you're looking at the edge, you might have 330 because you're actually measuring an indenter in the surface at the center. So you've got 20 degrees or something like that difference there. If you start looking at what happens if you put cement, you can see that there is a problem with the T-drop being larger even across the surface just using the cement. So strange things are happening. And if you put radiation from the indenter in front of the sample, then you get an increase in temperature above what you measure when the cup is away, as we talked before. And we have some very weird readings, which I don't understand at all about the outer one happening there. But what you can say for certainty is you can't take the hot stage control temperature. And if you want to take the inner temperature, well, that's a better indication. But of course, you can't stick a thermocouple where you want to indent. So you're likely to be able to be forced to use an edge thermocouple, in which case you could be 20 or 30 degrees out from where you think your temperature is. And that may or may not be a problem. So in essence, you have thermal gradients. I'm looking at this in one dimension. The thermal gradients are driven by the thermal conductivity and the heat flow. So if you've got an indenter and it's got radiation and it'll heat up the tip comes in, it'll heat up even more. And the power out is whatever thermal conductivity you've allowed to the rest of the world through your shaft, for example, outside of the hot zone. And that will determine, versus the power input, what the thermal gradients are here. Now, this surface temperature changes every time you change the sample. It's a different sample, different thermal conductivity, different thickness, different amount of cement, etc., etc. So it's difficult to find a way you can calibrate the temperature difference of the thing that you can measure here, or even the temperature of the surface that you might measure and the gradient that you might have. The most reproducible thing is to use the indenter, because that is a low thermal mass, a low heat capacity, but it's also unchangeable. If you move backwards and forwards with your indenter, you can actually see the effect of radiation quite readily. This is moving up backwards and forwards about 50 microns, I think. And you can see that there is quite clearly a change, which the inner thermocouple can just about see. The edge thermocouple doesn't see at all. And therefore you can see this radiative effect actually happening quite readily with a simple thermocouple. So if you look at the indentation again, you have a heat inside this, but your indenter tip is colder than your sample. What happens is now you suck heat out of your sample and you cause a local cooling, freezing. Now that's supplied by energy from the sample because there's energy coming from the heater. The heater down here is controlling to a constant temperature, but you get a gradient across here, and that gradient increases as the contact heat flow increases and as the sample thermal conductivity decreases. So if you've got a very good conductor, then this is a small gradient. If you've got an insulator, a ceramic or something that doesn't conduct heat very well, that gradient could be appreciable. Most of the things that you want to test at high temperature may well be of that sort. So this is an issue. If heat flows on contact, then you'll get a change in this gradient here, and you'll get a change in the temperature that you measure here. And so by going into contact and seeing if that changes, you can detect whether there is heat flow. So the way to calibrate that is to have a perfect sample that you can accept gives out a standard amount of radiation, so that when you indent into it, you can measure that offset. So you measure the offset when the heat flow is 0. So coming into contact, this doesn't change. That is a reproducible thermal condition. So that offset is a reproducible calibration. And the beauty about it is that you can argue as much as you like about what gradients would form in this sample if there was a heat flow. And it's all complicated and very three-dimensional. And the point is, if there's no heat flow, there are no gradients that you need to worry about because they're all the same. It's all at isothermal contact. So great. So we know how to do this. We've got a reproducible contact method. We've got a method of detecting whether we've got to the right thing. What we really need now are properties that are in a certified reference material at temperature. Well, at room temperature, we can go to NPL and we can obtain for a price their data sure reference materials. And they have a very low uncertainty in elastic modulus, and they give you a Poisson's ratio as well. And so you can look at your machine and you can check its working and look at its repeatability at room temperature. If you chop bits of it up and stick it on a hot stage, what you find is that you get a 12% change in frame compliance and a 7% change or so in the area function of your indenter tip as a function of the first 300 degrees of temperature that you increase. So, question, is this a measurement of the change in properties of the reference material as a function of temperature, or is this a change in the frame compliance of your stage as a function of temperature, or the thermal expansion or other change in your indenter as a function of temperature? You don't know until you calibrate your certified reference material. This can be done. So we, back in the day when I was at NPL, we actually developed them and we were on the point of selling them, and then I left NPL and they didn't actually commercially offer them, I don't believe, but we still have the capability, I believe, to do that, and we're looking to develop those in collaboration again with various research partners, including Micromaterials, so that going forward, when we have a standard, we can obtain an actual measured value. So I've run over time, I do apologize. But what I'm trying to say is there are some challenges to instrumented indentation testing, and you can meet those challenges. Just do the right experiment, respect the laws of physics and chemistry, make the best use of your experimental time, and maybe do some elastic modulus corrections. Calibrate everything, even if you think they should be constant, as a function of temperature. And as soon as they come on the market, invest in low uncertainty reference materials so that you can check what you're doing. And I have to thank all of the people who over the last 10 years contributed slides to this talk and the various European and national funding sources. So thank you very much indeed for listening. So Krish, I don't know what we do next.
Stage. Yeah, sorry, Nigel. I'm just working through the buttons to get myself back up on the screen. I need a bigger laptop screen. I think it's cutting off all the green buttons at the bottom. Should be used to that by now. Yeah, so there's at least one or two questions coming in. I think we'll take two or three and then move on. You actually weren't that far over. We started 5 minutes late anyway, so that's
Thank you.
Good. So a question from Guzi. It's this fairly fundamental question. We'll answer it probably between us. Why is the Micromaterials nanodentation is line flat? So this means why are we working with horizontal loading? The sample should stick on a holder with glue and stand it in front of the indenter tip, and not just using the what was referred to here as the normal holding way, like in a tribometer. Will this make high temperature tests more complicated in terms of nano indentation?
Okay, well, I can't. I mean, there's a Micromaterials response, obviously, that's possible to this, but as an external user looking on at this, that is what is done, and you can see why. It's a pendulum-based system, And so it applies forces around a neutral position where the pendulum is hanging from a flexure support. And so having the pendulum operating horizontally is the way all pendulum-based systems operate, Sharpie testers, etc. And so that is not an unexpected configuration. At high temperatures, it's quite interesting. In fact, you might argue that a horizontal configuration is a good idea, because it allows any convection of, if you're operating in gas, to go vertically between the two, the sample and the indenter, without going up into the sensor system of the display. Usually the force and displacement of sensor systems are above a vertically operating indenter. And so, yes, that's just the way it is. I think it doesn't really necessarily make a difference, because you're applying a force, you move the stage, and you're calibrating the force that you apply. So the fact that you've got gravity isn't a problem. Even if you have a vertically operating system, you cannot reproducibly mount a sample just by lying it on the top of your stage. So particularly not in the nano and the low micro. So you have to clamp it down or glue it down anyway. So it doesn't matter really whether it's vertical or horizontal.
Yeah, I'll just add to that, of the micromaterials side, that we've had 25 years experience of gluing samples down at high temperature. I like to think we're very good at it after 25 years. So we've all that experience and all that knowledge. And as Nigel indicated, even working in the other way around, you're likely to be gluing or clamping the sample down as good practice anyway. So in that respect, there's not so much difference, but the ability to have the thermal heat not go into your measurement system, or radiate into your measurement system, is one of the biggest advantages of working in that particular direction. If you've got any more questions on that, I'm happy to talk to you afterwards. So if you just send us a communication, and I can talk about that in more detail. There's one more question here. Actually, there's two more questions. This one's from Shashank. Hello, Shashank. Does RM value, dose RM values are limited with particular load and temperature, just like in Vickers testing with load?
I think that's reference material
values.
So I think interpreting that question is, are reference material values limited the particular load and temperature, just like Vickers testing with, well, so the difference between instrumented indentation testing and conventional hardness scales is conventional hardness scales allow you to test at a single force. Instrumented indentation makes a virtue of being able to test at a continuous increasing force and make measurements of displacement all the way along, and then you can choose where you stop. The properties that we traceably calibrate are elastic modulus, and their advantage of those are that they are insensitive to a lot of things that would otherwise affect hardness. So for example, size of indentation affects hardness. Things like that, residual stress is an issue that you might want to worry about, but it's actually a lower effect on elastic modulus. So if you look at elastic modulus, you can make any size indentation and expect to get the same elastic modulus, and so you are actually better off doing instrumented indentation from that perspective.
Good, thank you. I'll take one more question. I'll say we'll take two or three, just to keep the everything flowing along. From Andrew Bird. When assessing heat flow by bringing the indenter into contact with the sample, do you need to apply a sufficiently high load to allow heat to flow across by creating an appreciable contact area, rather than just resting the tip on the surface?
Okay, that's a very good question. And clearly, if you increase the contact area, you can increase the ability and the heat flow into your indenter body, which is what you're using as a thermometer. The thing is, if you're using a diamond has such a high thermal conductivity that you really don't need to have much of a contact for any difference in temperature to drive heat flow through that. So in fact, the temperature of the diamond tends to be pretty constant because it's such high thermal conductivity, and it just sucks out the heat locally from the spot it's touching. So yes, you will get a better and more intimate contact, and you will be more sensitive to a temperature difference if you increase the size of the contact. But if if you want to do that, that's fine. It's a bit like doing an approach indentation. You might want to do the sort of test indentation to one side, set everything up, and then move to where you want to indent and do the indentation there. But at the end of the day, the real problem comes if you're using something that's not a good thermal conductor as an indenter. We didn't get time to talk about that very much, but it is one of the issues that you have to consider in your indenter choice, because if you have an insulator as an indenter, then it's pretty difficult to measure heat flow.
Very good. Thank you, Nigel, for that talk. Well, I'll cut the questions at that point, but any questions that have been asked that haven't been answered will be collected by Sam, and we will get to you for direct answering. Appreciate it. Was a very informative talk as always, Nigel. Really appreciate you doing that.
Well, thank you very much for inviting me. I appreciate it. Thank you.
It's always a pleasure. The next talk is from Vinay Bakri. Vinay is a research scientist at the Canadian Nuclear Labs. Took his PhD in 2009 from Western University, which memory says is probably London, Ontario. And he's a very experienced user, and look forward to your talk, Vinay.
Thanks, Chris.
Okay.
Hi, Sam.
Sorry, Vinay, I'm just bringing your slides up. Just wanted to make sure to let you know, yes, we can hear you and everything. So please take it away.
Excellent. Thank you. Thanks, Chris. Krish, for the introduction. Before I start, I just want to ensure that, like, if audience can see my cursor moving, and if Sam can confirm it.
It was sharing from the platform. We can't do that. If you do require that, we can just quickly set up the screen share. Do you need to do that?
Sure, if that's okay.
Yeah, of course. So please go ahead and bring your slides up, because the start sharing will be the start sharing screen button, and you want to share your entire screen, please. You put,
sure.
You put just note for everyone, thanks for answering the poll questions so far. Let me answer, let me just release another one of those. And also to make it clear, as I said before, an attendance certificate will be available later in the event. I'll release the link for that then. And yeah, you will all receive a that is just the PowerPoint window that you can share your whole screen. Sorry. If you could just stop sharing that for a second. If you could reset this up, please. But to set it to share your whole screen, please, not the PowerPoint window. And then, as an additional to everyone, please type all the questions that you want in the chat. Chris will be taking as many as time allows, and then we'll so it should be the option when you're doing share screen, your whole monitor.
Can you see my screen?
Yeah, it's just the PowerPoint window. However, the standard PowerPoint window. Okay. Do you think it would be easy, just in the interest of time? Shall I just bring?
Yeah, please.
Yeah. Let's okay, I'll just bring up the slides as we had them. Sorry, everyone. If you can just indicate, describe on the slides. Sorry about that.
No problem, Sam. Okay. So, hello everyone. My name is Vinay Bakri. I'm from Canadian Nuclear Laboratories. As Krish mentioned, that I'm going to talk about high temperature properties of silicon carbide coating in surrogate triso fuel particles. First and foremost, I start by apologizing because of my odd voice. I'm coming out of really bad cold So you may hear a few cough during my talk as well. So I apologize in advance. Before getting into the talk, there are co-investigators in this work with me from Canadian Nuclear Laboratories. Hygrivan Mburi is a colleague, is a research scientist from Advanced Reactor Directorate. Rob Bayer is the nano indenter instrument lead technologist at Chalk River Labs. And Patrick Morrison is the metallographer who actually prepared the samples that I'm going to show and talk about in this work. So the overview for this talk, first, an introduction. I'm going to introduce trisofuel particles. I realize that the audience might be diverse. So this is specifically about these advanced fuels, trisofuel particles. I'll talk about them initially to introduce the fuel particle concept here. And then subsequently, the sample preparation, followed by nano-indentation system calibration check, which was very detailedly explained by Professor Janet before me. Then subsequently measuring the mechanical properties of as deposited and helium implanted silicon carbide coating in triso particles. And finally, I'll conclude the talk by summarizing the results or like the current results and ongoing work and current challenges that we have been facing for high temperature mechanical property determination on these silicon carbide coatings and trisofuel particles. So starting with the triso particles as fuel concept, triso stands for tri-structural isotropic particles. These are basically these multi-layer coated particles where the core is a fissile fuel kernel, which is coated with multi-layer or multi-layers of different materials, basically to encapsulate or capture the fission products within this 1 millimeter diameter fuel particle itself. I'll explain a bit more the function of each coating on the fuel kernel itself. But these small 1 millimeter diameter particles are actually embedded in silicon carbide or graphite matrix in the form of a pellet or in a pebble. So there are multiple of these small particles are embedded in these different geometries for them to be used as advanced fuels in high temperature gas reactors and molten salt gas reactors. The image on the extreme right that you see is basically a cross section of our triso particle showing different components of the particle itself. It's called surrogate because the kernel here is zirconium oxide instead of nuclear fuel, which is typically uranium oxide. And this is done for the developmental purposes. Like, so life is easier when you start simple. So we started developing methodologies to get the properties of these individual layers. And particularly, I'm going to talk about silicon carbide coating today with these non-irradiated and surrogate trisofuel particles. The same image now shows basically different components of the particle in the cross section. Kernel, which is typically nuclear fuel, uranium oxide, is 500 plus minus 50 microns in diameter. And it is coated with a buffer layer, which is about 100 plus minus 25 microns. And it's a porous carbon coating, which is there to capture any fission products, because like this is fuel, during its use in a nuclear reactor. There will be fission products, and the idea is to capture those fission products in this porous carbon coating around the fuel kernel itself. The next to it, the third layer that you see, which is a darker layer, is a high density carbon coating. It's called inner pyrolytic carbon coating, which is about 40 plus minus 10 microns in thickness. And the idea is that, like, say, whatever fission products are not captured in buffer layer will be captured by this high density carbon coating. On the top of this inner pyrolytic carbon layer, or the high density carbon layer, there is silicon carbide coating, which is there to basically provide the structural integrity to this entire component. And the coating thickness is also about 40 microns plus minus 10 microns. And the final coating on this particle is again high density carbon coating called outer pyrolytic carbon coating layer, which is there to protect silicon carbide layer itself. The operating temperature for these fuels is about 1,000 to 1,200 degrees C when they will be used in reactors. So we need information on the high temperature mechanical properties of these different layers around the fuel kernel. In particular, I'm going to talk about today silicon carbide layer at reactor relevant operating temperature to accurately model the fuel performance itself. So now, since these are only 1 millimeter, approximately 1 millimeter diameter particles, they're extremely small, and the problem is more complex when there will be irradiated fuel. So the normal handling of these specimens will not be possible. We are dealing with, we are coming up with methodologies to handle both the situations. The first one here, where, like, say, we are looking into unirradiated surrogate trisoparticles. We have come up with a specimen preparation method where we start with this preparing a 3D printed donut-shaped mount. And then in the second image on the top, you see basically we have these tiny trisoparticles sitting on a double-sided tape with this 3D printed mount on top of it. In the third image on the top, you see we pour a high temperature cement, omega 600, and let it cure over 24 hours to slightly longer. And then at the bottom left, what you see is basically these trisoparticles embedded in the high temperature cement mount within this 3D printed puck that we have. The multiple of them, and then we take this cement puck out of the 3D printed mount and use our metallographic polishing routine to polish these pucks with the high temperature cement mounts with multiple trisoparticles to a final polishing level of 0.02 micron silica level on the diamond pads. Post-polishing, we look at the metallography and the microstructure of the polished samples. What you see on the top left is a low mag image of a polished cross-sectional image for the particle. At the bottom, you see these different components. What we see is that, like, there is a bit of debonding between the kernel and the porous buffer layer, and sometimes we see some cracks in different parts of layers, constituent layers of the particles itself. On the right, what you see in the left image is an SEM image where there is a silicon carbide layer embedded in the carbon coatings, high density carbon coatings on either side. Left side is the outer polyoliptic carbon layer. The right side is inner polyoliptic carbon layer. In this image, you can actually see these are as deposited coatings. There are some pores. These are the deposition defects in the material itself. On the right, there is an EBST map that is overlaid on this area. This a particular type of silicon carbide coating is a cubic silicon carbide coating, 3C type. What you see in this EBST map towards the right, which is the interface with the inner polyoliptic layer, the grain size of the silicon carbide coating is actually smaller, and the grain size does increase as you go from left to right, from inner polyoliptic side to outer polyoliptic side of the particle itself within the silicon carbide. And at the bottom, you see the grain size distribution. Typical grain size near the one edge of the coating is between 0.3, 0.5 microns. And as you go towards the other end of the coating, the grain size becomes extremely large, sometimes greater than a micron, or sometimes even 2 microns or so. So we prepared sample. We looked at the metallography and the microstructure of the material itself, and now it's time to start testing the sample. And as Professor Janet very articulately described the importance of calibration of the system before testing, and I must admit that, like, say, we adopt similar methodology, but like, say, which is starting with load calibrations, depth calibrations when needed, and the diamond tip area function, which is characterized on routine basis before and after testing in our lab. But we do only this at room temperature. We do not do the calibration checks at high temperatures, but that's something as the continuous improvement we would like to adopt going forward. So before we start testing, we do the system calibration check on a reference material, which is fused silica, and we tested the silicon carbide coatings in the initial run only up to 300 degrees C. Although the pursuit is to go up to the reactor relevant temperature up to 1000 to 1200 degrees C, but as the challenges involved with extremely high temperature indentation, we have started to generate this data set for these silicon carbide coatings in TRISO for this moderately high temperature up to 300 degrees C. On the top left, what you see is the schematic of our system, where we also use 2 independent heaters to heat the specimen, and in this case is fused silica, sample provided by Micromaterials, and then the indenter tip itself. We do use a secondary thermocouple on the top of the sample near edge, not exactly where we indent, but this is just to minimize the gradient, the temperature gradient between the tip and the sample surface, the indenter tip and the sample surface. So we performed load control tests to maximum load of 50 millinewtons, and I'll come to this specific value of 50 millinewtons, why we chose this. But it was used for fused silica. as well as for our silicon carbide coatings. Results I'm going to present subsequently. So we use these maximum load, so the load control indentations up to maximum load 50 millinewtons. The loading rate was 10 millinewtons per second, and the dwell at the maximum load was 5 seconds, and subsequently the indenter was unloaded at the same original loading rate, which is 10 millinewton per second. So the total experiment time to load, hold, and unload was 15 seconds for these experiments, and the thermal drift measurements at the end of the experiment was the time that we used, where we held the indenter tip barely touching the sample, or at 10% of the maximum load as specified by Micromaterials, is for 30 seconds. On the box on the right, on the top, what you see is the load displacement curves from room temperature to 300 degrees C for fused silica. As expected, the displacement at the maximum load of 50 millinewton increased with the increase in temperature. And the plastic depth at room temperature was around 300 nanometers, and the thermal drift that we measured for room temperature measurements was the order of minus 0.01 nanometers per second. This is the best we can achieve within our lab itself. But when we consider this 0.01 nanometer per second negative as thermal drift, and the total duration of the experiment, which is 15 seconds, so it means the drift contribution in our total displacement data was quite less than a nanometers, 0.15 nanometers, where the plastic depth was around 300 nanometers for these elements. Similarly, at 300 degrees C, the plastic depth for fused silica measurements was for 50 millinewton maximum load was about 360 nanometers, and now the thermal drift that we measured was slightly higher than room temperature, was minus 0.06 nanometers per second, but for 15 seconds of experimental duration, the total contribution of the thermal drift to the plastic depth was still less than a nanometer, which was I consider like insignificant. So using these load displacement curves at different temperatures, we extracted hardness and reduced elastic modulus for the standard fused silica over room temperature to 300 degrees C. And you can see the hardness versus temperature. Our data is in blue triangles, room temperature 150, 300 degrees C. So the hardness did decrease with increasing temperature, and it aligns very well with two previous studies, one by Ben from Micromaterials, and another one by Chris Xu from MIT on fused silica itself. So our measurements on fused silica are well within in agreement with the literature values. On the other hand, the reduced modulus values, again, our data is in the blue triangles. The reduced modulus increases for fused silica with increasing temperature, and this is because of the fused silica is amorphous, and there's increasing viscosity with the increasing temperature. And the similar increases have been reported by, again, both Chris Xu et al. And Ben and Jim Smith in the previous group. So basically, getting similar trends as in the literature, and the right ballpark for hardness and the reduced modulus on the standard specimens. We deemed ourselves as ready to move on to actual testing on silicon carbide coating and the trisol fluid particles. Here, now from this slide, the message is that, let's say, now we kept we tried to do these experiments fast. When I say fast, they're not exactly very fast, but like they're still 15 seconds. And based on the discussion that I had here about the thermal drift measurement at different temperatures and relative contribution in terms of the depth from drift to the total plastic depth and the influence on the measured properties. So faster you do the experiments, lower the chances, or like say lower the thermal drift contribution is. Now, as I said, that like say 15 seconds, although I say it's fast, but recently I see some dynamic indentations where like they're extremely fast indentations. Literally, you can do thousands of indents, or you can do indents in a fraction of a second, which is extremely fast, which might be okay for less strain rate sensitive materials, but like in case of metals or like say higher strain rate sensitive materials where your properties are dependent upon the rate at which you actually load your specimen are dependent on the strain rate itself, then it can be problematic. So it's just a caution for rate sensitive materials to do extremely fast indentations. But for silicon carbide, which is ceramic, now when I mentioned, like say we did use 50 milliliters as a maximum load, the idea was that like say since we're going to perform these indentations on a ceramic coating, so which was brittle, so we need to know what the maximum load that we can actually use to without cracking to perform our indentation testing. So we optimize the maximum load for as deposited silicon carbide coatings and surrogate triso particles. We perform room temperature indentations with varying load from 50 millinewtons to 200 millinewtons. And on the top that you see is the hardness versus load response on the left. At 50 millinewtons load, there were two different particles that we used. The hardness was 30 plus GPa, 35 and 32, 33 GPa at 50 millinewtons, but hardness did drop with increasing load. Ceramics typically don't show the size effect as the metals do, where in metals you see the increase in hardness with the decrease in load or indentation depth. So this decreasing hardness with the load was coming from something else. Similarly, for the elastic modulus, as Professor Janet was explaining, that like the elastic modulus is a material property, so it should not change with load or depth. But in this case, what you see is that the elastic modulus is changing with the increasing load. And when we looked at the indents in the SEM, we saw cracking around the indents, which were greater than 50 millinewtons, 100 millinewtons and 200 millinewton indents has very clear cracks around the edges of the indents itself. And the hardness is a plastic property, so any cracking in your around your indents actually invalidates your experiment for the hardness measurement. So the 50 milliliter indentations were at room temperature were crack free. So we chose 50 milliliter as a maximum load for these measurements. Moving on to some results from as deposited silicon carbide coatings. You see on the left is hardness versus temperature. We got the surrogate triso particles from two different suppliers. The data is in red circles, solid circles, and blue solid circles. So first, from supplier one, the elastic modulus, the hardness for these silicon carbide coatings from supplier one was about 40 GPa on an average at room temperature. And for supplier two, again, the hardness was slightly lower, but was still close to about 34 GPa or so. These extremely high hardness values are typical of ceramic coatings, in particular at room temperature, where the lattice resistance is still very high and results in this high hardness values. And as the temperature increased, the hardness did increase did decrease with the increasing temperature, and it's consistent for both supplier 1 and supplier 2 supplied trisoparticle silicon carbide coating. And with the increase in temperature, what happens is that, like say, when the lattice resistance is very high at low temperature, room temperature, and as you increase the temperature, that lattice resistance drops, so that facilitates the dislocation motion, and the hardness does drop, and that's what we actually see. So our data here from two different suppliers agrees well with the literature values from 2 other independent investigations in the literature. In the elastic modulus results with temperature on the right, the supply 1 particle, again in the red circle, solid circles, over the temperature range, we don't see much of a change in the elastic modulus, and it was of the order of about 350 GPa for the coatings from supplier 1. The material itself has very high melting temperatures, about 2800 plus degrees C. I was expecting to see a slight drop in the elastic modulus over 300 degrees C, but the fact that like our experimental measurements do not see the trend. But I'm hoping it might be related. I'm not sure. I'm just speculating. Probably the maximum, the valve at the maximum load might be the reason, or so the expectation is that, like say, we probably need to modify our the existing the testing parameters, or like I'm hoping that, like say, with further increase in temperature, we'll start to see a decline in the elastic modulus for these coatings. So for supplier 2, the modulus was slightly lower. It's the order of, like say, 250 GPa, and it was again consistent over 300 degrees C, was insensitive to the temperature. And again, there are measurements from the reference for the elastic modulus for the silicon carbide coating, and we are within the right ballpark range here. One thing which I want to point out here is the assumption that, like say, we have been using the Poisson's ratio for cubic silicon carbide, which is 0.14, to measure the elastic modulus of these coatings from the reduced modulus that was actually provided or measured by an indentation system. Now, when eventually these particles will be used in reactor where there will be neutron irradiation. Because of the neutron irradiation, there will be irradiation defects which will be produced in these constituent layers, including silicon carbide. And also there will be transportation effects where there will be hydrogen and helium production within the silicon carbide coating itself. So we wanted to look at the effect of the helium the produced helium due to the irradiation on the performance of the silicon carbide coating. On the right, what you see is a literature or the literature results where the helium implantations were done in 6H silicon carbide single crystals at different temperatures. And what you see is, because of the helium, you start to see some nanobubbles forming within the material at 450 degrees C and at 600 degrees C. And at 750 degrees C, these bubbles become, like say, elongated in shape and were extremely big. So to start, what we did, like say, we did some helium implantation in the surrogate trisoparticles and silicon carbide coating from supplier one. Like say, using an ion accelerator at Western University in Canada. So we used a multi-energy beam from 200 keV to 1300 keV to perform the helium implantation at room temperature. What you see on this in the left box, top right image, there is a helium profile distribution in silicon carbide coating layer, silicon carbide layer, where from about 1 micron to about 3 microns, there was about 1000 ppm, APPM level of helium was there. And we used these helium implanted sample 50 millimeter loads to the maximum depth that was reached. We found that, like, say, the plastic zone of the maximum depth was covering this 1 to 3 micron depth of the damage, or like the helium implanted zone that is expected as predicted by these string calculations here. And the results from as deposited and helium implanted from supplier one coatings. First, again, the red circles from as received coating at the hardness did decrease with the increase in temperature, whereas for helium implanted sample, hardness did drop from about 40 GPa to about 37 GPa for helium implanted sample, but as the temperature increased, the hardness did not change as much. On the right, what you see is the elastic modulus, where the elastic modulus for the as deposited coating was about 300 GPa, again insensitive to the temperature. With the temperature change, was overall it was dropped to about 260 GPa and again remain insensitive. So there was overall decrease in the elastic modulus for helium implanted coatings, but again it remains insensitive to the increase in temperature. And this may possibly be coming from the fact that, like, there might be a nanoporosity that is forming within the localized region, as I was showing in my previous slide, which is causing the elastic modulus to drop. But to know the exact reasons, we have been pursuing the TM analysis of the specimens taken from the indented sites and also away from the indented sites for these samples from both helium implanted as well as the as deposited silicon carbide coatings. So to conclude, we're developing methodologies for sample preparation and testing of these constant layer. In particular, what I talked today was silicon carbide coating and surrogate trisofuel particles for high temperature measurements, and for as deposited silicon carbide coating, hardness decreased with increasing temperature up to 300 degrees C. Temperature changes had no effect, no significant impact on the elastic modulus. And for helium implanted coatings, hardness did not change substantially with temperature up to 300 degrees centigrade. And overall elastic modulus for these helium implanted sample compared to the as deposited coatings was lower, but again it was insensitive to the probe temperature range. And these results are part of the effort to contribute to develop a comprehensive material property data set for trisofuel performance or for the modeling purposes itself. The ongoing work and the current challenges, and as I was explaining earlier, that the intention is to measure the properties of the silicon carbide coatings to relevant temperatures up to 1000 degrees C, and the challenges as very well laid out by Professor Janet. First is to find out the stable indenter tips to go to these extremely high temperatures. The second is finding a suitable high temperature mount material for tricer particles. Right now we are using high temperature cement, which we notice, like say around 500 degrees C or above, the cement starts to disintegrate. So we need more suitable material for to mount these tricer particles, to prepare and subsequently test. And third one, last but may not be actual last, is the reference sample, which we can actually use for the system calibration check and the tip area validation itself. So this work is ongoing, and I'm looking forward to collaborate with the industry itself to basically to overcome these challenges as we continue our pursuit to make these measurements at extremely high temperatures. Finally, before I close, I acknowledge Canadian Federal Science and Technology and Lab Directorate Science and Technology and the ST programs at CNL, Canadian Nuclear Laboratories, for funding this research. Thank you very much.
Thank you, Vinay. I appreciate the talk. Thank you for the information. We're running a bit, but let's take one question from Alex. Alex is asking, did you see any variation across the silicon carbide layer? Was there an influence of the adjacent PYC layers, which are soft, very soft and compliant in comparison?
That's a very good question, Alex. We all these measurements were made right exactly in the center of the coating, or relatively in the center of the coating. Coating was about 40 microns wide, so about like say 20 microns from either edge. But we do plan to look at the variation of the properties from one edge to the other, where like as I was showing, there is a difference in the grain sizes, smaller grain size near the interpyrolytic coating layer, and as you go towards the outer pyrolytic layer, the grain size becomes larger. So we do expect to see some changes, but we haven't looked at the results yet. But that's part of the plan.
Thank you, Vinay. Thank you for that talk. Very much appreciated. We will get other questions to you after the event, just to keep things moving along. The next talk we have is from Lucas Kapaska. He's head of material research at the National Centre for Nuclear Research in Poland. I think been there since 2020, having finished his PhD the previous year at AGH Krakow. So I shall hand you over to, he's going to talk about iron chromium model alloys at high temperature after radiation damage using nano indentation. So Lucas, thank you very much, and looking forward to your talk.
Thank you, Krish. Thank you for inviting me here. First of all, can you hear me well? Can you hear me? There's no problem?
Krish? Yes, we can.
Okay, perfect. Perfect. Sorry, let's start. Good morning, good afternoon, or good evening. My name is Łukasz Kurpaska. I come from National Center for Nuclear Research. Today, I will tell you a little bit about how we use nano-indentation to understand different deformation mechanisms in model iron chromium and iron nickel alloys. Particularly, I will focus on dynamic strain aging and how we use this technique to understand radiation damage buildup in those alloys.
Apologies, everyone. Just slight technical hiccup there. Łukasz, can you come back on stage, please?
Yeah.
Sorry, I might.
Yes.
Possible So I misclick. Is everything okay now?
Yeah, perfect. A few words from where I and my team are from. So as I said, in the National Center for Nuclear Research, this is where we work. It's a research institute in Poland, located 35 kilometers southeast from Warsaw. We employ more than 1,000 people, have a wide and vast collaboration across the world. And my team particularly is interested in radiation damage, understanding radiation damage resistance and mechanical properties of materials. We are doing this and building these capabilities at NCBJ because Poland is entering nuclear family. We decided to build generation 3+ PWR reactors. And we observe that nuclear has been recognized and come back again to the picture to fight and combat climate change. Both European Union as well as different countries, they recognize together with quite famous visionaries this technology as a way to provide carbon-free energy. Generation 3 reactors is part of the solution, how to combat climate change. There is a concept of generation 4 nuclear reactors, which are characterized by much higher efficiency in terms of electricity production. However, all the concepts in the frame of generation 4 nuclear reactors, they require operation at much higher temperatures. The materials must sustain much higher damages, and they are cooled with very aggressive media, like liquid lead, for example. Therefore, conventional materials, steels and alloys, they swell, we observe helium embrittlement, and they are prone to failure. That's why we need to develop new materials, and this is what we are doing at NCBJ. How to do that? Well, when you have a material, you can either put it into the reactor core and test it, how it behaves afterwards, after irradiation, or you can use ion irradiation. Ion irradiation basically means you are shooting into the material with energetic ions, and by collisions of the atoms, which are caused by interaction with this ion, radiation damage is being created. This radiation damage caused by ion radiation mimics radiation damage caused by neutron irradiation. There is one pitfall of this technique. The radiation damage profile is quite narrow. Usually, we manage to change the volume of the material, which does not exceed more than few microns. Therefore, we are creating something which is called a thin layer inside of the material, and we need techniques which allows us to probe both mechanical and structural properties only from this irradiated layer, and this is where nanoindentation comes quite handy. Because this technique allows us to collect elastic deformation from the whole region, from the whole irradiated region, without interference of unirradiated bulk material. Then, with the help of other techniques like transmission microscopy, all or modeling parts done through various different techniques, we can delve into a quite complicated physical phenomena occurring due to the interactions of radiation damage defects with dislocations. At NCBJ, we are using a high temperature system, which allows us to heat up the samples up to roughly 800 degrees. It's a purge system, and today I will present you a few results from these measurements. Another motivation for studies at high temperature is that there are very few data on how materials behave at temperatures exceeding 550 degrees. Therefore, me and my group, we position our research on testing at in situ at high temperatures, just to understand what is the behavior of the material in the operating condition of the given material. Today, I will tell you a little bit about three research examples. I will start from model iron chromium systems, which represent martensitic ferritic steels, and I will describe how we use nanoindentation to design new high entropy alloys which are resistant to radiation damage. So first, ferritic martensitic steels, which basically means very often Eurofer 97, are considered as a candidate material for structural components of the next generation nuclear reactors. However, these steels are not perfect. They show problematic irradiation-induced embrittlement, especially at low temperatures, and loss of ductility. Therefore, we need to understand what happens with these materials at high temperatures. And to do that, we decided to do a few steps back and produce model materials containing only iron with 9% chromium, and the system with addition of solid atoms. By conducting tests, the same tests, both irradiation and high temperature on each of these four materials, we are able to isolate features which are responsible for hardening effect. And by progressing between those model materials, we increase compositional and structural complexity, which allows to isolate the responsible mechanisms of hardening. It is very important to pay attention to the chemical composition between the samples we tested, as the only elements which changed are carbon, solid atoms like silicon, phosphorus, and nickel, as well as chromium. I will relate to this slide a little bit later. So we did our nanoindentation using cubic boron nitride indenter on model iron chromium systems and Eurofer 97. The measurements were done at 200, 400, at 600 degrees. They were repeated roughly 15 times. As I said, we used purged chamber, the chamber which was purged with high purity argon, just to limit oxidation. And the total measurement time per sample was roughly three days to conduct all of this. As Nigel said, it is not necessarily easy to limit oxidation, as we could not record the signal for pure iron at 600 degrees, because at this temperature iron oxidizes very rapidly and very easily. When we analyzed the low displacement curves, we saw that there are certain bumps, or one may say steps, and these steps appear periodically, and we noticed that they appear only on a certain temperature per given material. So to understand a little bit better the origin and the magnitude of those steps, we plotted derivatives of the displacement time curves, and yet again we saw that these bursts in our work, we call it the bursts, they appear only at 200 degrees on iron, and we see them at 400 degrees when we test iron with chromium and iron chromium with solid atoms at 400. Although at 400 for the iron chromium with solid atoms material, the volume of those or the magnitude of those bursts is much lower, and they do not appear in Eurofer 97. So what is really going on? In the next step, we plotted hardness and Young modulus values in the function of temperature, and we saw that whenever the bursts appear, the hardness do not drop. Actually, it either remains at the same level in comparison to the previous temperature measurements, or even increases. And this is particularly visible for an iron 9% chromium when at 400 we saw a significant increase of the hardness value. So in the next step, we did detailed transmission electron microscopy analysis below the indents. And apologize for amount of text, but what I want to say is that depending whether we tested, we observed indents measured at room temperature or at high temperature, we saw that dislocation networks appear on sides of the indents in the case of iron and iron 9% chromium, or we see dislocation forest networks in the case of two more complicated alloys. And this is happening at room temperature. When we go to high temperature, we see that dislocations arranged to form polygon structures in model materials, whereas in the commercial Eurofer 97, there is a grain recrystallization and transformation of elongated grains to equiaxed grains. So the next step was to calculate the dislocation density, and obviously there is a huge difference between non-deform and deform at room temperature dislocation density below the inlet in the material. However, we did not see a huge increase of dislocation density after high temperature indentation. Moreover, Eurofer 97 showed significant reduction by almost 40% in terms of dislocation density compared to the measurements done at room temperature. So we did some reading, especially we checked some simulations of those systems, and we noticed that as I said, and we checked the chemical composition of all the materials, and we saw that in the case of iron, there is a carbon in the system. The carbon amount is in a ppm level. However, this is enough for carbon to migrate and diffuse at certain temperatures. And this is what is happening at 200 degrees, because 200 is enough for carbon to diffuse and lock dislocations, which are generated due to deformation. So these bursts observed at 200 degrees for iron is basically means that carbon is blocking movement of the dislocation. This phenomena is not occurring for iron 9% chromium and the same material with addition of solid atoms at 200, because we have chromium in the system. Chromium is known to have a much stronger affinity to carbon than iron, and basically creates complexes composed of chromium and carbon. These complexes, they cannot diffuse at 200 degrees because the temperature is too lower, but the diffusion starts at 400, and this is what we see again at 400 degrees, that carbon chromium complexes are diffusing to the proximity of the dislocations. They are locking their movement, preventing from spreading around, and the bursts we observe are due to this interaction and release of the deformation suddenly when the critical point has been reached. The absence of those bursts in Eurofer 97 is related to the martensitic microstructure and presence of other solid atoms in the Eurofer 97. And this phenomenon is known as dynamic strain aging, and usually it is studied by using tensile tests. However, with this work, we proved that it is possible to use nano-indentation and demonstrate the presence of this phenomenon. It is quite important to understand when this phenomenon is appearing in the material, because this DSA effect limits ductility of the material as well as impacts fracture toughness, decrease the fracture toughness of the material. Just to say a few words how to delve deep into mechanisms of interaction of dislocations and radiation damage defects. We often use help of our numerical teams, and it is quite interesting that this field is developing very fast, and right now it is possible to model volumes of the material composed of more than 100 million atoms, which basically means that one can model volume of few, even tens of cubic nanometers, and these are the volumes which are achievable by very precise low load indentation. So we did this benchmark exercise, and we tested. We wanted to understand what is happening within the nickel-iron system, as this is a model. These are two basic elements from which high entropy alloys FCC structure are being built. In this case, we noticed that when we increase the amount of iron in the material, we observe hardening. And we checked the transmission electron microscopy, and we observed that there are stacking fault tetrahedra created when we deform material. However, we didn't know how they are being created. What is the road towards creation of those features? And by exchanging information with the numerical team, we come up to the conclusion that these are basically prismatic dislocation loops in interaction of them, which leads to the creation of those features. As I said, this was confirmed by transmission electron microscopy and allowed us to understand what is happening with nickel iron within the nickel iron system. Ion irradiation is one part of the story. Another part of the story, when one deals with nuclear energy, is temperature. And we submitted the same alloys into the. We basically annealed the same alloys, and we saw that only the effect of the temperature results in hardening measured by nanoindentation. So what's going on? Again, we went into more deeper structural studies by using synchrotron and high-resolution TEM, and we saw that FCC lattice, because of the temperature, reorganizes itself and creates L12 or L10 phases, which limit dislocation motions. And these local reorganized structures, they are responsible for the recorded hardening effect. As I said, numerical modeling is quite handy, and we recently proved that there is a migration of chromium atoms in the proximity of dislocations developed due to nanoindentation, and those chromium atoms, they limit motion of the dislocations, which is causing the hardening. This is one step to understand better behavior of Eurofer 97 in the nuclear environment. So quickly, I will tell you about two examples of high entropy alloys we are studying right now. I will start from demonstration that by doing macroscopic tests, we can get similar results as within nanoindentation. So this work is being done in collaboration, European collaboration called INNUMAT, where we are developing cobalt-free high entropy alloys, which application will be in next generation nuclear reactors. And in this work, we are doing high temperature tensile tests. When on the miniaturized dog bone specimens, you see on an image here that we are testing 8.6 millimeter length dog bone specimens. And again, at a certain temperature, we saw a very similar results as within nano indentation on the previous examples. When doing tests at 400, 550, and 700 degrees, we clearly see that only in one temperature the stress strain curve is showing some kind of discontinuities. There are certain bumps on this curve. At the same time, when we plotted mechanical properties in the function of temperature, we clearly see that suddenly the drop is not that dramatic in this temperature. So we believe that this is again dynamic strain aging, which is caused by solid atoms. We are doing right now precise chemical analysis of the alloy to understand on the ppm level what is going on with this material. But this demonstrates that nano indentation in the nanoscale can be quite easily compared to the macro scale measurements. And to conclude with radiation damage resistant studies, I want to bring your attention to two examples of high entropy alloys we are developing. We hypothesize that when we put a lot of stable nanostructures in the form of nanoprecipitates and small grains, we will create big density of grain boundaries that will pin dislocations and consume both vacancies and interstitials produced by radiation. Therefore, we want to build a material which is resistant to swelling and hardening by introducing a lot of nanostructures. For this purpose, we manufactured single crystal alloys and alloys with the precipitates. We submitted them in collaboration with our US partners to irradiation at 580 and 700 degrees. Please pay attention that these are operating temperatures of generation 4 nuclear reactors, and irradiation was done up to 120 dPa. This basically means that by conducting this irradiation, we mimic the end lifetime of the material in the nuclear environment. And then we did nano indentation to understand what is the hardening effect. And to our surprise, we saw that the hardening between non-irradiated and irradiated specimens is only 25%. When we check the literature, similar composition of steels show 50, even bigger than 50% hardening with only fraction of radiation damage. So we demonstrated that these materials can operate at high temperature, at very high damage doses, without being brittle, because this is one of the biggest challenges in nuclear energy. We want to avoid brittleness of the material. We explained this phenomena that in this system, stacking faults, they contain vacancies which are then consumed by grain boundaries and dislocations present in the material. And here, nano indentation came very handy to understand this. To test this hypothesis. Another work, when we increased slightly chemical complexity by adding chromium to the system, again we conducted similar irradiation, and in this case we basically did not observe any hardening at all. We see that there are some dislocations, the radiation damage defects created by irradiation, but the total density of dislocation didn't change significantly. And when we analyzed microstructure following the increase of the irradiation dose, we did not see any voids in the material. So to conclude, nano indentation, can be truly used as a helpful tool to understand radiation damage resistant of materials, as it allows to test small volumes. Since we are not able, and there is a very limited amount of nuclear reactors, research reactors, which are capable of doing neutron irradiation, we are forced to do ion irradiation, which basically creates a small volume of the irradiated material, and here nanoindentation comes quite handy. And the data recorded in a nanoscale can be quite easily. There are some challenges, however, it is comparable with the macroscale tests, and support, as Dr. Vinet also showed, support from structural analysis side and numerical simulation comes very handy. However, I must admit I enjoyed very much presentation of Nigel. There are some pitfalls in this technique, and one should carefully do the nanoindentation to get the results properly. So with this, I would like to thank you. First, I would like to thank all the co-authors from Material Research Laboratory and Nomaten Center of Excellence, which is currently funding our work, for the contribution and for help in getting those data analyzed and tested. I also thank you, Micromaterials, for inviting me. It's a pleasure to give a talk and work with you. Thank you.
Thank you, Lucas. Thank you. Appreciate it. We've got time for a couple of questions that have come up. First one is from Samir. He asks, how did you prepare the high entropy alloy, and can high entropy alloys be built in bulk size and quantity to replace urethane in potential applications?
Yes. So the model high entropy alloys with large grains were prepared by arc melting, while nanocrystalline high entropy alloys with addition of precipitates were prepared by spark plasma sintering.
Okay.
Technique, yeah.
Okay, and then a question from Taylor. Do you expect annealing? Do you expect annealing away of irradiation defects when nano-indenting to elevated temperatures and above irradiated temperatures?
That's a very good question. This is our next step. So for the moment, we did the high temperature measurements were done only on non-irradiated specimens, and of course there will be we expect annealing of defects at high temperature when you heat up the system. However, I would strongly recommend doing that in a vacuum system, which basically prevents from oxidation, because with irradiated layer you must remain in a volume modified by ion irradiation. Therefore, your indentation should be quite shallow. If you have nanometers, tens of nanometers layer oxidized on the surface sample surface, you may have to take into account first when analyzing the data. But yes, I expect some annealing of the defects at high temperature. However, this is our next step to do this work. Yeah.
Okay. And then from Chandra, Chandra is saying, as far as I know, nano-indents are smaller than grains, and tensile test provides us with the property of polycrystalline material, which is affected by grain-boundary interaction. Chandra is wondering how, if nano-indents are conducted on multiple grains as well as on grain boundaries.
Yeah. So all depends how deep you are go and what kind of material you are testing. When we tested, it's true that high entropy alloys, for example, after arc melting, they may show quite big grains, and then your information represent basically given grain orientation, and we see fluctuation on mechanical properties per grain orientation. However, when you test nanocrystalline material with the grains, and the examples I showed where the average grain size was about 50, 60 nanometer in size of the grain. We tested, we went up to 200 nanometers deep. Therefore, we collected information from about 2 microns, maybe a little bit more, which basically represents interaction of tens of grains, and then the interaction with the grain boundary is included in that.
Lovely. And this quick one from Nigel. Have you tried the Euroatom project indentation side effect fingerprinting of the damage?
I don't. I think he means about M4F project. I will have to check that, because I am working with Peter Hanner, who helps also to take into account basically indentation size effect in our studies. So I will thank you for that. I will I will check this. Yeah.
Lovely. Thank you, Lucas. Thank you for that presentation. It's appreciated.
Thank you.
And,
thank you very much.
very good. Okay, so we move on to James next. James Gibson. James took his DPhil from Oxford 2015, having graduated initially through Corpus Christi in Oxford. So remember, worked over RWTH Aachen from 2015 to 22, coming back to Oxford, well, to the Cullum UKAE Oxford University, some sort of combination of that, back in 2022. And I shall hand you over to his talk on pushing the limits in nanomechanical testing, which is something that we all would like you to do. Thank you very much.
I'll try my best. Thank you very much for the introduction. So this talk is going to be a fairly light-hearted look at the sorts of things we've been doing over the past 10, 15 years or so, including our trip up to testing at 1,000 degrees. So we will run over some of the pitfalls that we fell into to hopefully mean that you won't do the same. So because this testing has been taken sort of a decade or more, I've had the pleasure of seeing the nanotest system evolve from its very early sort of custom setups in Cambridge and the system in Aachen to the more commercial systems first installed at Oxford, and then here on the right, the ones you can see that you can buy today. And there's a key theme in all these systems that have this very large vacuum chamber installed in them. And that really is critical when you start pushing temperatures up above that sort of 200, 300, 400 degree limit, particularly when you're working on reactive metals. So I've spent a long time working on tungsten. It's the tiles you see on the left here are candidate plasma facing tiles for future fusion reactors. But unfortunately, tungsten loves oxygen. No matter what you do to it, whether you test it in an inert argon atmosphere, a reducing helium hydrogen atmosphere, or if you stick other metals in like zirconium into your vacuum chamber to do your very best to soak up all the oxygen, your tungsten will eat it. And when you have the sort of 2 micron irradiation damage layers that we've just seen, that you're really interested in testing, this oxidation ruins them. It completely destroys them. And so we found very early that it's absolutely vital to test in vacuum when we go to these very high temperatures, where you can see that we have this pristine sample here on the right for these sorts of temperatures and these sorts of reactive metals. So everything you see here will have been done in vacuum. And what I'll show now is kind of the work that we did trying to get our system up to hit that 1,000 degree nice round number milestone. So this one we actually didn't do on tungsten. We were a bit bored of it by then. So we had a look at nickel superalloy instead. This was made by our colleagues over in Forschungszentrum Jülich, which has got this nice 001 crystal orientation, much like you would see in application. But the thing we were interested in is this Amdry 386 bond coat that sits on top of it. It's got this nice fine equiax microstructure. And this is really the glue that holds the yttrium stabilized zirconia on top of our nickel superalloy blade. So it's very important in practice that this glue is nice and strong. And we need to know what its mechanical properties are up at high temperature. So we took a sample of this, we thinned it down, we polished it up, as you can see here, and we started kind of plugging power into our indenter and trying to see how hot we could get it. But very quickly, we actually ran out of power completely. And what you can see here is a plot of temperature versus heater power along our x-axis. In red, you can see what happened to our samples, furnace, stage, and the enormous gap you see developing as we go up in power is due to the really poor thermal conductivity of the sample. This was a millimeter thick sample, which is pretty thin as samples go. But even at relatively modest temperatures of 500-600 degrees, you've got a 200-300 degree gap between what you're plugging into your heater and what eventually reaches the top of your sample. Now, this wouldn't be a problem, except that when you want to hit those 800, 900,000 degree temperatures, your furnace starts to melt before your sample gets to those degrees. Your tantalum heater wires have an upper limit of about 1300 degrees. And so this really does limit you in how hot you can get your sample. Is can you actually get enough power in without melting your heater system? In fact, more problematic is in fact what happens to your tip. So these are AFM scans of pristine Berkovich from the literature, and what happened to our indenter after 4 indents at 1000 degrees. And this is enough to take the measured hardness from half a GPa up to 4 GPa. It's basically ruined. It's turned into this horrible blob, and means each indent costs about £800, I think, from memory, which is not very cost-efficient testing. So you see this huge amount of deposition, this huge amount of chemical reaction, and that really is what we're finding at these high temperatures, is what the limiting factor is for high temperature nano indentation. There's a tentative answer that tungsten carbide is probably the best choice for indenter. It's pretty hard. It's not as hard as diamond, but it's still pretty good mechanically. But by and large, what we care about at these temperatures is not mechanical performance, it's chemical performance, and that's where it comes in. As long as you're testing in vacuum, you can use this tungsten carbide indenter, and that shouldn't react with most samples that you're interested in. So then by making a very thin sample, a few hundred microns thick, and testing very quickly so we didn't ruin our indenter, we managed to get these data points for our superalloy, which we can use as a reference here in black, as well as the bond coat that we care about. We see that we get comparable mechanical properties for our superalloy and our bond coat all over all ranges of temperatures, which was very nice. It means we shouldn't be developing any thermal stresses. And we see the hardness temperature behavior is pretty close to literature. Now, those of you who like a superalloy will notice that there is a problem with pretty close, in that whilst we maintain our indentation hardness up to about 400 degrees, a real superalloy should keep its strength up to about 800 degrees. So what's going on? Why is there this 400 degree discrepancy between the small scale and the large scale? Well, it's not a size effect problem for once in our nano indentation lies. It's actually a crystal orientation problem. Those literature data where we see strength up to 800 come from tensile testing and 001 oriented single crystal. So you're only activating a specific set of slip systems. Actually, when you've got a nano indenter, you've got a much more complicated stress state. You've got this hemispherical set of plastic deformation under your indenter tip. You're activating all your available slip systems. You've got very high stresses, and so your dislocations can cross slip. And so what you get, in fact, is cross slip and deformation on much softer crystal slip systems. And you can see here the gray lines, the gray dashed lines, are what happens when you test those high strength gamma prime precipitates in different crystal orientations. And actually, the bar 111 orientation softens past 300 degrees. And so this is exactly what we're picking up with the indenter. It's simply a crystallography effect where we're getting softening by having slip on our weakest available slip system. So that kind of explains the hardness data. What about modulus data? Well, that kind of turns out fine most of the time. For sort of up to 700 degrees, where creep rates are relatively limited, we're pretty much bang on with literature data. At 900 degrees or 1000 degrees, we're measuring nonsense. There isn't another way to put it. There is too much creep left in our unloading curve, even after a very long dwell period, even unloading as fast as we can. In fact, we work out if we want to unload fast enough to beat creep in this, we need to be unloading at 300 millinewtons a second, which is far too fast for our electronics to keep up. We get no data in our unloading curve in that case. And so that, oh, hold on. So that kind of explains why the 900 and 1000 degrees are a bit low. We're measuring a creep effect. We're not having that elastic unloading that we need for reliable measurements of modulus. We can also fit to that hold segment in the middle and hopefully extract something with creep. Now, ideally, that whole period is not just to make your modulus sensible. Ideally, it will give you something that is vaguely related to creep properties in reality. And we see actually here that we don't do too badly. This might be luck, but we don't do too badly. In our reference CMSX4, dinickel superalloy, we do capture the temperature dependence very well. You can see the kind of literature gradients marked out in blue compared with our indentation gradients marked out in red. We do have a shift, probably because of that complex stress state, but we do capture the temperature dependence of our creep stress exponent. For our fine polycrystalline bond coat, that's most likely why we get this much closer match in both the orientation and temperature dependence of our creep stress exponents in our nickel bond coat, which is very good. It means we can then move on to materials development and really understand that the sorts of creep exponents that we're getting at these temperatures might actually be relevant for then application design as well. But really, the takeaway from these tests is that what we found is there's kind of no one ring to rule them all of high temperature nano indentation testing. I'm calling high temperature nano indentation testing where creep then has a significant influence on the mechanical properties that you measure. You're kind of stuck between deciding whether, at least if you're doing one test, whether hardness is more important for you, in which case you need to be doing a very short hold at peak, or whether you'd like to have a long creep hold period at that peak load, let that creep dissipate, measure it, understand it, and then have more accurate elastic modulus measurements. The reason why you don't want a long hold for the hardness is demonstrated kind of best by work out of Leoben. This is comparing continuous stiffness measurement with load hold tests, but the principle remains the same. Essentially, once you start doing that load hold segment, is that your strain rate then starts dropping. And so because your hardness is dependent on strain rate, what you measure will be a strain rate at the end of the test, but what you think you've done is a strain rate at the start of the test. And you don't need a very strain rate sensitive material. Things like iron or coarse grain zinc, titanium, these are all this circled bit, this sort of middling strain rate sensitivity. And these can lead to errors in this 5-second hold period of up to 10%, which is quite significant for quite such a short hold period at room temperature. You can expect that difference in hardness, that uncertainty in your hardness measurement, to be increasing even more once you're up at very high temperatures where these creep rates are significant. So then if I move on, this is now micromechanical testing. This is all work that Bo did during his PhD. He was also looking at tungsten, these lovely plasma-facing tiles, but he wanted to understand their fracture properties. We're interested in tungsten, which unfortunately sits around the mechanical properties of glass when you look at its fracture toughness. So understanding that our fusion reactor will not shatter when we apply a load to it is obviously quite important to us. But we're limited, as we've seen, from having to use iron irradiated material, which limits us to trying to mechanically fracture test samples that will only be 2 or 3 microns deep in order to remain within that radiation damaged layer. And the technique that Bo came up with is this really elegant chevron notched microcantilever geometry. So it's based on this pentagonal cross section milled out using the focused ion beam. So you can mill it anywhere in your surface. You're not limited to using just the edge of your specimen. So you can get much more efficient use of materials. But the real trick he came up with is this chevron geometry of the pre-crack you induce near the fixed end of the beam. And so by milling out this sort of triangular chevron geometry at the top, you have a very, very high stress intensity factor right at the surface of your beam, where your bending stresses are also highest. So you kind of automatically pre-crack your sample. You end up with a very, very sharp crack, self-inducing almost from the surface. So you don't have to worry about fib damage in your crack or whether your crack is fast enough for valid fracture toughness measurements. The other nice thing is then, because your cross-sectional area increases, that stress intensity factor drops, and you get very stable crack growth, and you can study that as your crack grows very slowly through your cantilever. And this is quite nice especially for tungsten, which is just about plastic enough not to show full brittle behavior. It's plastic enough we have to use the J integral and elastic plastic measure of fracture toughness to evaluate its fracture toughness. And so by using these load partial unload tests where the load is gradually ramped up and reduced, you can track through that stable crack growth, crack extension, the changing compliance of your cantilever. You can build up this crack growth line and therefore evaluate this elastic plastic fracture toughness. Now, when you take these tests up to high temperature, especially when you want to take them to very long time scales where you're looking in more almost into a low cycle fatigue range, your experiment time gets very long, several hours per test. This is one that a relatively quick one that only took 2 hours. And you can see the raw data implies that we've got about 250 nanometers of permanent deformation. Actually, the micromaterial system is extremely stable, and thermal drift rates are low enough that a simple thermal drift correction after the test collapses most of this load unload low cycle fatigue behavior on top to a single curve. And so the drift corrected data only showed 90 nanometers of permanent deformation, which then matches up very nicely when we start using the indenter like an AFM, taking this topological scan of our cantilever after testing. And you can't tell within the color scheme, but you can believe me when I say the end of that cantilever is now only 90 nanometers below the surface. So we can kind of combine these two things, this clever chevron notch geometry, as well as this very, very stable system, to start doing ductile brittle transition temperature studies. So on several beams at several temperatures, we can take it up, we can extract our elastic plastic fracture toughness and our stable crack length. We can plot these out therefore as a function of temperature and understand how our ductile brittle transition temperature changes as a function of material or eventually as a function of radiation damage. One of the really nice things that Bo showed is that the micro and the macro BDT are very, very close to each other. There is a small difference between in the kind of raw number between the micro data and the macro data, but that can be attributed to the higher strain rates in the small scale testing, as well as the fact that we're looking at a tungsten tantalum alloy rather than pure tungsten. But essentially, we can conclude from this that the brittle ductile transition temperature does not show a size effect, which is an absolute wonder for small scale testing, where everything else really does. So that brings me to the end. They're kind of fairly simple conclusions. High temperature testing is not straightforward. If anyone of you have tried it, you will know it's not just regular indentation where you turn the heater button on. It really requires robust hardware. At the very high temperatures, it really requires reaction-resistant indenter materials as well. I've shown you from the superalloy studies that anisotropic single crystals behave very strangely in indentation. It takes a while. You have to be aware of them. But there is some evidence that at very high temperatures where you have significant primary creep, you can get real kind of creep data out of fine polycrystalline materials. And you've just seen that when we do these tests on tungsten up at higher temperature, there's no size effect in its ductile brittle transition temperature. So that, thank you very much for your attention. I'm very happy to take any questions you have. Thank you.
Thank you, James. That's great. It was nice summary of many years' work, to say the least. So I've got a question here from Nigel. They're talking about the Berkovic that scanned in the AFM. Is it made of sapphire?
Yes, that one you see on the slide here. Yes, that was a sapphire one. We did this early enough that we didn't have the availability of things like a tungsten carbide indenter yet. So this one was sapphire.
Okay, very good. Okay, I think that's the and okay. So there's a question from Tan. Let's see, thanks you for the talk. And it says, may I ask about UKAE's capability to handle radioactive materials for performing indentation testing at room and high temperature?
Yes,
presumably you have some.
so
You have some, presumably.
we have several. We have 3.5, I guess, depending on how you count them, nano indenters that are equipped to handle active material. It's a question of how active each sample is. If you drop me an email, I can give you some more details. If they are so active, they have to be sort of robotically handled in a hot cell. That's a lot more challenging than maybe a proton irradiated sample. The short one is yes, we probably can do it. Drop me an email to discuss more, please.
And then from Alex, have you tested any other materials at cryogenic temperatures for DBTT?
Me, not personally. I think Katie Plummer tried to do some cryogenic moly on the Oxford system. I don't know how well that went. It's certainly possible if your DBT is below room temperature. It's the same principle.
Yeah.
I've not done a lot of cryo work personally.
Okay. Well, we have been looking at some cryogenic measurements elsewhere, and maybe Alex will take that. I'll answer your question offline on that, basically. Okay, James, thank you for that. Appreciate that. I've got one extra small talk that has appeared, which I think Ben is going to give now, if he's online. If he's coming onto the table.
Just invited to the stage. It should be very remote.
Okay. So this is a short talk on some general high temperature testing principles. I shall leave Ben for you to talk about that now. I should just introduce Ben properly. So Ben is our Director of Applications Materials, and at Micromaterials he's a visiting professor of a couple of universities, and has 270 odd papers to his name. Just to put some, has worked for Micromaterials for 20 years plus. I'm not going to be exactly how accurate, but beyond that number. Okay, thanks a lot, Ben.
Thank you very much, Krish, and thanks. So I wasn't quite aware what James and the others were going to talk about. But this is very, very quick rattle through just to get across the fact that although high temperature testing is challenging, then we do have these capabilities to do other tests apart from just nano indentation. So you heard from James using things like microcantilevers cleverly to look at brittle ductile transitions. There are other things you can do to pull out changes in yield stress and things like that. So you can also do micropillar compressions and other type of tests, tribological tests. So I'm going to give just a few sort of examples of those in this very brief presentation. So one of the things that I think has been maybe just mentioned in passing is that we have this integrated nano-positioning stage option, which allows us to accurately both do fast indentation mapping, but also to do accurately targeting for specific grains and or to basically to position the indentation or the pillar compression or the cantilever bend exactly where we want, which we need for the maths, and also allows us to do image to create the images with the tip, and that's what you need therefore to really accurately position that for these sort of measurements. As well as that, you can do tribological tests, small scale scratch tests, small scale impact tests, and so you have a wealth of different information that you can do with these high temperature tests. Excuse me. Sorry. So I won't wish to say again about James's wonderful work on the left there, but also just to show more recently how we've extended that work to get similar stress exponents on other superalloy systems again. So that really backs up the sort of consistency between these different measurements. So one thing that we haven't really talked about so far is how to do mechanical properties of coated systems as a function of depth. So this is also possible at high temperature if you have a thermally stable system where you've minimized your heat flow. And here you can see an example here on a very thin amorphous carbon coating, which is slightly harder and stiffer than the glass substrate at room temperature, but as you can see here, as it's heating up, then its near surface properties have degraded somewhat. So just to really get across that we have this sensitivity to do these very small scale measurements as well. And the same methodologies that ISO 14577 Part 4 suggests you can do at room temperature, you can apply these same sort of things to high temperature. So one thing that we're working at the moment in collaboration with a university in Canada here is on micromechanical mapping at high temperatures, indentation mapping at high temperatures, and this is just an example here at 200 degrees Celsius where we're doing very small indentations into a multi-phase alloy which has these intermetallic phases in, and we can track how the different phases in that material, how the temperature dependence of their mechanical properties quantitatively by producing these array maps. So Vineet said earlier that one of the important things with these Triso particles was to minimize cracking. So that is certainly the case if you want to measure the variation in the hardness and the stiffness of these things as a function of temperature. But one of the relatively useful things as well in the nanotest system is having this availability of this relatively high load. So in this case, the group in this case in Manchester have got relatively low load measurements on the left to get the mechanical properties, hardness, elastic modulus, function of temperature. But on the right, they used a higher load specifically to look at fracture toughness in these. In this case, it's a bulk CBD, but the same sort of measurement idea that you can basically look at fracture and again as a function of temperature. So an alternative approach to, as James was talking about with the chevron notched beams. So these nano-positioning stages allow you to accurately position and target specific phases. So in this case, there's some work done by MPL where they've indented into certain phases, and they know exactly which USD know exactly which phase is which, and then they can see how the mechanical properties of the different phases in the material, in this case it's cemented carbide, vary as a function of temperature. Okay, so yeah, certainly James has talked a fair bit about these deformation of beams. So this is a much simpler, earlier version at the University of Oxford, where they were just looking at single bending of beams to fracture and looking at temperature dependence there. That one, as James has talked about, so I won't really say any more, apart from the fact that it's the stability of the instrumentation that allows these long duration multi-cyclic testing. And then say a methodology approach from heating up, imaging the surface, then doing the testing is a very simple workflow in the nanotest system. So moving on briefly to the tribological stuff now. So here's a work just recently finished project with the UK Space Agency, where we're now looking at small-scale wear testing at high temperature. So in this case, this work was done as in looking into the properties of MOST-based thin films for space applications. And in the results, so you can see on the right there, then essentially that's just showing you have the stability to do these 1,000 cycle tests quite easily and look at things like the friction coefficient and the depth and see how those vary as a function of cycles. So in this case, you can see for various different coatings that there's big difference in stability in terms of the number of cycles before the friction coefficient goes up as the film starts to fail. So this is much older work now. Here, this is going back to sort of the original test would maybe sort of 2004 or something like that. So here we're using microscale scratch testing. So again, looking at, in this case, PVD coatings for cutting tool applications. And if we test this coating in a multi-pass scratch test at room temperature, then it after a few cycles, you can see these localized failures in the coating, and essentially it's delaminating in certain regions. If we do that same test at high temperature, then it was more resistant. And subsequent to that, we could understand how what was causing that in view of how the failure location was changing as a function of temperature due to the mechanical properties of the system changing. So that's something where we're using indentation and scratch data together to improve our understanding. So again, it's this multifunctionality in the system. So more recently, we've started to play around with high temperature impact testing. So one of the things we've been doing is as James mentioned, thermal barrier coating systems are quite an interesting thing to look at. And one of the things we've done is we've done our so-called randomized impact tests. So in this case, we're doing a cyclic test, but between each impact, we're moving the sample in a designed programmed array. And then in this case, there's just one example there shown in the middle, and that creates this high temperature damage. And what you can see on the right is the surface of a thermal barrier coating that's been impact tested in this case at 850 degrees C. And this sort of cracking and compaction is similar to what you see in eroded samples. And you can look at more brittle systems. In this case, this is just a few silica glass, which, as Vineet said, it's slightly unusual, anomalous temperature dependence and elastic modulus. And interestingly, actually, also its fracture behavior undergoes clear transitions. So in this case, this is just cyclic tests at the same position, but you can see a clear difference in behavior when you test 400 degrees and below, and then at 650 degrees, you're getting a transition into a much more gradual damage deformation mechanism. So there's a lot of new things that we're starting to look at, but we're not fully understanding, but we have the capability there in the instrumentation. So hopefully that wasn't too long. It's just to give a general overview of the exciting things that you can do in the nanotest advantage and extreme systems that are not just the indentation capability. Okay, so thanks very much. That was it from me. So quick that somebody else. There you go, Chris has come back.
Thank you, Ben. Thanks. Quick overview of a wider range of measurements on the high temperature. There is a question in from Yanné in France. At high temperature, how do you use notched cantilevers? If not, how do you get a crack initiation, given that the material becomes more ductile? Which is actually a very good question, I think.
Well, I think James answered it quite well. That Bow's test technique really did have this notch geometry that really sort of was a critically useful thing in terms of getting the there you go. So you can sort of see right there in the middle there. Then he's created this Chevron geometry, and there's a very slow extension of that small crack in the middle there that's being studied in the test. So obviously there were different types of geometries that you can use, but I think the work that Bo and James as well have done at Oxford and UKEA is giving us lots of confidence about that you have this flexibility.
Okay, yeah, just get the window out the way of the middle. Lovely. In the absence of any further questions, it remains for me to close the workshop, to say thank you for everyone who's attended, everyone who's come in, and everyone who's attended throughout. You can find out more about us at our webpage, materials.co.uk, or you can get to the company LinkedIn page, which is a very good source of information. It will contain future invites to these type of seminars, invites to actual real seminars, face-to-face seminars, gives you information about papers and publications that are published by our users, plus news about micromaterials and where we're going, where we've been, and who we're talking to, which is always good to know. Yeah, make use of it. It's a good resource. It's a very, very technical and gives you a lot of stuff. I'd like to thank Micromaterials for organising this, Alison and her team, marketing department. Thank you to all the speakers who have attended today, because without them this would not be anywhere near as interesting. And thank you for attending, and I wish you all again good morning, good afternoon,
and
good
thank you very much to Sam for the organisation as well. Much appreciated.
Oh yes, yes. We say Sam for that as always. I appreciate that very much. So thanks a lot, and yeah, goodbye.
Thanks everyone. Bye bye, and thanks to Krish for the hosting as well.